A Category 4 hurricane can fit its worst winds into a tight core. A Category 2 can spread dangerous weather across hundreds of miles. If you only compare the category numbers, you can rank those storms backward. The category is useful. It tells you how violent the strongest sustained wind is near the center, but it does not tell you how large the wind field is, how much rain is coming, or how high the ocean may rise. Imagine two spinning disks. One is small and fast. The other is slower at the center, but broad enough to drag a much larger patch of ocean and atmosphere toward land. Their numbers favor the first. Their footprints may favor the second. That mismatch matters because a hurricane is not one speed. It is a moving system with an eye wall, outer bands, waves, rain, and a circulation that can reach far beyond the point where maximum wind is measured. So what does the category leave out, and how can a storm that looks weaker on the scale produce a wider, longer, or more expensive emergency? The answer runs through three storms with very different shapes: compact Hurricane Charley, broad Hurricane Ike, and the extraordinary wind field of Sandy. Once those storms sit on the same map, the category stops looking like a complete score. It becomes what it was designed to be, one important measurement inside a much larger machine. That distinction changes how we read every forecast that follows. A lower category can mean the peak wind eased while the circulation widened, the rain slowed down, or the coast became more exposed. The digit can move one way while the emergency moves another. The Saffir-Simpson Hurricane Wind Scale sorts hurricanes from Category 1 through Category 5, using maximum sustained wind speed. That is the definition. The scale estimates the wind damage that the strongest part of the storm can produce. In the Atlantic and Eastern Pacific, the number comes from the highest 1-minute sustained surface wind assigned to the cyclone. It is a peak value, not an average across the whole circulation. That peak usually lives in or near the eye wall. Move away from that compact ring and the wind normally weakens. A category therefore describes the top of the wind profile, while most of the storm occupies the slopes below it. The familiar thresholds are sharp. 74 miles per hour begins Category 1, 96 begins Category 2, 111 begins Category 3, 130 begins Category 4, and 157 begins Category 5. A 1 mile per hour change across a boundary can change the category label while barely changing the physical storm. Meanwhile, a large change in size can transform the hazard footprint without changing the category at all. The National Hurricane Center states this plainly. The scale does not include storm surge, rainfall, flooding, or tornadoes. It also does not encode coastline shape, forward speed, or the duration of damaging conditions. The category answers one clean question: how strong is the storm's strongest sustained wind? To understand the rest, we need a second measurement that rarely fits into a headline. It is tempting to stretch a simple scale until it answers everything. That makes communication easier for a moment, then hides the details that determine who floods, who loses power, and how long dangerous conditions remain. Simplicity helps only when its boundary stays visible. Forecasters describe hurricane size with wind radii. These are distances from the center to threshold, such as tropical storm force or hurricane force wind, measured separately in different quadrants because real storms are rarely perfect circles. A storm moving north can pile its forward motion onto winds on one side while subtracting from the other. Nearby weather systems can stretch the circulation. Land and dry air can carve chunks out of it. Put those radii together and a footprint appears. That footprint tells you how many miles of coast may feel strong wind, how long conditions can last, and how much ocean lies beneath persistent onshore flow. Size can change independently of peak intensity. A hurricane may weaken at the center while its outer wind field expands. Energy spreads outward, and a compact core becomes a broad circulation. A wider storm also takes longer to pass a fixed point. Even if the local wind is below the peak, hours of stress can damage trees, power lines, roofs, and coastal defenses. Over water, the footprint controls how much surface the wind can push. A broad field has more room and time to build waves and move water toward shore. Now the hurricane has two axes instead of one: intensity and size. Category occupies the vertical axis, footprint occupies the horizontal one. Two storms with the same category can land in very different parts of that grid. A compact major hurricane sits high and left. A sprawling lower category storm can sit lower and far to the right. Add forward speed and the picture gains a third dimension: how long each part of the footprint stays over one place. On August 13, 2004, Hurricane Charley accelerated towards southwest Florida. Near landfall, reconnaissance supported Category 4 intensity, with a tiny closed eye wall only about 5 miles across. That compact core concentrated extreme wind into a narrow corridor. Places that crossed the eye wall suffered catastrophic damage. A short distance away, conditions could be dramatically different. Charley's small size made the exact track unusually important. Shift that tight ring by a few miles, and the zone of the most destructive wind shifts with it. The storm also moved quickly. That limited the time any one location remained under its most intense rain and wind, even while the compact eye wall delivered a severe local blow. On a map, Charley's Category 4 label looks enormous. Draw the actual inner core to scale, and the geometry changes. The highest category occupied a much smaller area than the number suggests. None of this makes Charley safe. It explains the shape of its danger. The storm behaved like a narrow blade, extremely sharp where it crossed, with a smaller zone of peak wind than many weaker storms. Keep that compact footprint on the left side of the screen. Next to it, we will place a lower category hurricane whose wind field covered far more ocean. The comparison is not a contest over which storm was worse. It isolates geometry. Charley demonstrates how a very high peak can occupy a narrow area. That narrowness made precise track changes matter intensely for southwest Florida communities near the eye wall. Hurricane Ike entered the Gulf of Mexico in September 2008 with an unusual structure. Its inner core was small, yet its broader circulation expanded into a vast wind field. Near Texas landfall, Ike was assigned Category 2 intensity. If the category were a total danger score, that number would suggest a problem well below a Category 4. The physical storm told a different story. NHC discussions stressed that Ike was very large and that damaging winds and dangerous surge would extend far from the center. Every additional mile of onshore wind gave the storm more ocean to work on. The broad circulation pushed water toward the Gulf Coast long before the eye crossed Galveston. Hours before landfall, official discussions reported water already 9 to 12 feet above normal across parts of the northwestern Gulf. The center was still offshore. The ocean had already responded to the footprint. Ike produced a devastating surge, with high water marks in some locations reaching roughly 15 to 20 feet. Local depth, coastline shape, and the storm's track all helped set those levels. Charley carried a higher category and a tighter core. Ike carried a lower category and a much wider push. One scale number cannot express both geometries at once. Ike's broad field also meant deterioration began far from the eventual landfall point. Coastal communities could not safely use the distance to the eye as a countdown. The storm was already applying force through wind, waves, and rising water. Wind transfers momentum into the sea through surface stress. Each gust pulls on waves and currents. Over a broad area, millions of small transfers combine into a moving mass of water. The distance over which wind blows across water is called fetch. A wider, persistent wind field creates a longer effective push, allowing waves and currents to organize before they reach the coast. Deep water can circulate downward as well as sideways. Near shore, the bottom interrupts that circulation. Water that cannot continue downward piles upward and inland. A broad, gently sloping continental shelf gives the incoming water less depth and more distance over which to accumulate. A steep shelf changes the result. The same hurricane can produce different surge on different coasts. Approach angle also matters. Winds aimed directly toward a concave bay can funnel water into a narrowing space. A glancing approach may distribute the push differently. Peak wind still matters because stronger wind increases stress. But surge depends on the whole setup: intensity, size, speed, track, shelf, tide, waves, and local geometry. Expand the wind footprint on our diagram without changing the category. The patch of moving ocean expands with it. The category stays fixed, while the potential coastal load grows. This is a systems problem because no input works alone. A wide storm approaching a steep coast at a poor angle can produce less surge than expected. A similar storm aligned with a shallow shelf and narrowing bay can concentrate far more water. A hurricane also transports water vapor. Rainfall depends on moisture supply, storm structure, terrain, and especially how long bands remain over the same place. A fast hurricane can move its rain shield through quickly. A slow or stalled storm can reload the same watershed for days, even if its peak wind weakens. Outer rain bands can extend far beyond hurricane-force wind. They can train over communities that never enter the eye wall and may sit outside the most dramatic wind graphics. The first rain soaks into soil. Later rain meets ground that is already saturated. Runoff accelerates, streams rise, drainage fills, and each additional inch has fewer places to go. Hills can force moist air upward and intensify rainfall. Urban pavement sends water toward drains faster. River levels may continue climbing after the center has moved away. Category does not capture any of that. A tropical storm or lower category hurricane can become a major flood event when its motion and moisture line up with vulnerable terrain. Swap the category badge for a clock. The wind number fades, the rain duration grows, and the map fills basin by basin. The hazard has changed dimensions again. Flooding can also outlast the circulation that produced it. Water needs time to move through soil, streets, streams, reservoirs, and rivers. The storm may disappear from the weather map while the watershed is still assembling its largest response. In October 2012, Sandy grew dramatically after passing the Bahamas. Its tropical storm force or gale force wind diameter reached about 870 nautical miles before landfall. Sandy's structure was changing as it interacted with a mid-latitude weather system. The inner tropical core weakened at times, while the broader wind and pressure fields expanded. Shortly before reaching New Jersey, Sandy completed its transition into a post-tropical cyclone. That classification change did not shrink the ocean already in motion or erase the enormous wind field. The circulation covered a huge stretch of the western Atlantic. Onshore winds, waves, tide, and coastline geometry combined across a region much larger than an eye wall. The storm's track drove water into New York Harbor and nearby coasts. The consequences came from a particular alignment of size, direction, timing, and local geography. A category label was never built to summarize that system. It could describe peak tropical wind while Sandy was a hurricane, but it could not contain the expanding field or the coastal response. Watch the center dot remain small while the wind field grows beyond the frame. The storm's most important change is not a higher number, it is the scale of the machine. That scale connected places that might otherwise seem unrelated. A wind field hundreds of miles across drove waves, coastal water, and power impacts across multiple states. A center-focused view could not show how much of the Atlantic had joined the event. A hurricane's fastest winds circle a pressure gradient near the core. When the inner structure changes, that concentrated ring can lose speed. Energy does not always disappear immediately. Angular momentum and convection can redistribute outward. The core relaxes while winds spread across a larger radius. Interaction with fronts or upper-level troughs can also broaden the pressure field. The cyclone becomes less symmetric and less purely tropical, but its circulation may cover more territory. This creates the paradox visible in Sandy and other large systems. The official peak wind can fall while the number of people experiencing damaging wind or coastal flooding rises. The ocean also remembers earlier wind. Waves and currents built over many hours do not vanish when the maximum wind drops by one category. That is why forecasters track wind radii, arrival times, surge inundation, rainfall, and local watches separately. Each product answers a question the category cannot. On the size intensity grid, move the storm down and to the right. The category falls, the footprint expands, the total hazard does not follow a single arrow. This outward redistribution is one reason a weakening forecast does not automatically mean every hazard weakens at the same rate. Peak wind can respond quickly to inner core disruption. Waves, currents, saturated ground, and infrastructure exposure have memory. Start with the wind layer. It has a compact maximum, broader hurricane force radii, and an even larger tropical storm force envelope. Buildings experience whichever part of that profile passes overhead. Add the surge layer. It depends on onshore wind across water, the seafloor, the coast, the track, and the tide. Its highest values may occur away from the point of landfall. Add rainfall. Its footprint follows bands, moisture transport, terrain, and storm motion. A slow storm can keep loading one basin after peak wind has weakened. Add waves and wave setup. Breaking waves raise the average water level near shore and strike structures on top of the surge. Add tornado risk in outer bands. These are usually brief and localized, but they occupy another region that a single central wind number cannot show. Where layers overlap, consequences compound. Surge blocks drainage while rain falls. Waves ride on elevated water. Wind damages the same infrastructure needed to move and pump water. Stack the transparent layers over one coastline. Category lights only the peak wind layer. The rest of the system remains visible, active, and impossible to rank with one digit. The layers also interact. Wind can remove roofs before rain enters. Surge can disable roads before the strongest gusts. Power loss can stop pumps during the flood. The outcome depends on sequence as well as the maximum value in each layer. Begin with the official advisory, but do not stop at the category. Read the forecast track, the stated uncertainty, and the size of the wind field. Check the arrival time graphics and local wind warnings. They show when preparations become unsafe and how conditions extend beyond the center line. In coastal areas, use the NHC Storm Surge Inundation Map and local evacuation guidance. Surge zones follow elevation and water pathways, not category boundaries. Read rainfall forecasts and flood products. The location of the eye does not define the full rain shield, and rivers may respond on a delayed schedule. Local National Weather Service offices translate the broad forecast into specific wind, water, and timing concerns for each area. Forecasts change as aircraft, radar, satellites, buoys, and models add evidence. New information can alter the track, intensity, footprint, and hazard layers separately. Replace the single category tile with a dashboard, peak wind, wind radius, surge, rain, motion, and local terrain. The storm finally has enough dimensions to resemble the thing approaching the coast. This dashboard is not a home-built replacement for official guidance. It is a way to read the products forecasters already issue. Each panel comes from a dedicated forecast, and local emergency managers combine them with evacuation routes and community vulnerability. Return to our first two storms. The compact high-category core and the broad lower-category field are both dangerous, but they are dangerous in different shapes. Charley shows why a narrow corridor can receive extreme wind damage from a small, intense eye wall. The track decides who meets the blade. Egg shows why a broad Category 2 can move an enormous area of ocean and spread damaging conditions far from the center. Sandy shows how a changing cyclone can expand beyond the neat language of tropical categories, while the coastal threat keeps growing. The category did not fail in those storms. People asked it to answer questions it was never designed to answer. It measures the strongest sustained wind and nothing more. For a real storm, follow official forecasts and local emergency guidance. Look at the whole hazard stack, especially surge and rainfall, rather than treating a smaller number as a smaller emergency. A hurricane is a field, not a point. Keep the category in its lane, add the missing dimensions, and the apparent contradiction disappears. A weaker number can belong to a larger threat. The number remains valuable precisely because its job is narrow. It communicates peak wind damage potential. The wiser response is not to discard the scale, but to place it beside the wind field, water forecast, rainfall outlook, and local instructions that complete the storm.